Well, we did draw the magnetic field lines. We said that they are circles around this. Okay, this is a magnetic field line. This is one magnetic field line. They just form circles around this axis, just like the right-hand rule. Okay, so your friend's question is this one. Okay, we only consider the change in the electric field at that point. You see, at that point, and we didn't consider the current passing through the surface. If you remember here, no, not this one. Now, to calculate the electric field at this point, we are using this relation. B dot dl around any closed loop is equal to mu 0 times I plus mu 0 epsilon 0 d phi E by dt. This is what we use to calculate the magnetic field at this point. Well, but we only considered this term. We didn't consider the first term. So we just ignored this term. We only had this one. But you see, if you consider at this instant, what is the current passing through this area? 0. I is 0. Of course, even if you take any arbitrary surface, eventually this current Q will pass through it. So at that instant, you will get this contribution also for an instant. But at this instant, I would rather choose a surface in which the Q doesn't pass at this instant. It will simplify my calculations. The result will not change. And furthermore, although we used this disk to calculate this electric flux, this flux also doesn't depend on which surface we choose also. Because you see, I chose such a surface to calculate my flux. Well, I could have chosen this other surface to calculate my flux. But I know that they have to be equal because in this volume, there is no charge. So whatever flux passes in this direction through this area should also pass in this direction through this area. There is no charge over there. So the flux, whichever surface you choose, will be the same, will have the same value. Other questions? Now we also, I always say that, okay, the physics is local. Everything changes only what is happening in the near vicinity. I cannot affect you instantaneously directly. It should be only indirectly. Now, if we take this charge, point charge over here, and if I move it over here, I know that the electric field over there will change. Now we also have a mechanism how that change comes about. Before we didn't have that mechanism before including this displacement current. You see, these are our equations. E dot ds is equal to Q over epsilon 0. E dot dl is equal to minus d phi b by dt. B dot ds is equal to 0. B dot dl is equal to mu 0. I plus epsilon 0 d phi e by dt. So as we are moving this charge, why does the electric field over there change? Well, if I move this charge, it changes the electric field nearby. So just close to this charge, I have a changing electric field. But this changing electric field creates a magnetic field at that point, at the nearby point. Now this changing magnetic field creates an additional electric field in the nearby points. So if I move this charge, it will change the electric field at this point, which will create a magnetic field at that point, which will create the electric field at the next point. And so point by point, this change that I created by moving this charge will eventually reach where you are. So you will measure a change in the electric field. Now the next question. How can we describe this change, this propagation? Now let us, if I have a charge over here, if I look at this volume, the charge is over here. Here there is no charge, there is no current. So the electric field in this volume, they should satisfy the Maxwell's fields in vacuum. So they should satisfy these equations. E dot ds is equal to 0. E dot dl is equal to minus d phi b by dt. B dot ds is equal to 0. B dot dl is equal to plus. Okay. So in vacuum, I have these equations, almost. Now in vacuum, this is 0, and this is 0. So these are the equations that we have. So whatever electric and magnetic field you are talking about, it can be an electric field created by a charge somewhere over here. They can also be moving. They will be creating a magnetic field. In this region, the electric and magnetic field lines have to satisfy this equation. Now let us assume some solutions. Now how do we get these solutions? We will not discuss that, but let's just for the sake of simplicity assume that in a region of space, now what we are trying to do is I'm trying to guess a solution of these Maxwell's equations, and I will see if they satisfy the Maxwell's equations. I'm not driving the solution, I'm just guessing. Let's say that we have an electric field which is pointing in the x direction only. It has a magnitude, let's call it E0, and it has such a dependence. And then I have a magnetic field Okay, so we have this electric field in the x direction. And the magnetic field, let's say it's in the y direction. No, this is z. Now, how did I get this solution? I'm just guessing. So is it possible to have such a solution? Is it possible that this equation these electric and magnetic fields, do they satisfy these equations? That's what we need to guess. Or if they satisfy these equations, what are conditions on E, B, K, and omega? What are they? Now, omega, we will just assume it's just arbitrary. Now, what is this equation to start with? Now, let's forget this one. Now, this is what we call a wave. That if you plot cosine kz minus omega t, let's say at t equal to 0, this is our z-axis, it just looks like this one. This is at t equal to 0. It's just at t equal to 0, as you move, look at different points, its magnitude just changes as a cosine function. Now it just repeats itself as you move along the z. It will repeat itself, and we call this the distance through which it repeats itself is the wavelength. This is what we call the wavelength. Now at t equal to 0, when z is equal to lambda, this cosine is again 1. This is 1, this is minus 1. So that tells me that cosine k lambda is equal to 1, or k times lambda. It's either 0, it cannot be 0. That means lambda is 0, we know lambda is not 0. K times lambda should be 2 pi. This is how k and lambda are related. So if you know k, you know the wavelength. Now, as t increases, as time increases, this whole pattern will be moving towards positive z. So this is at t equal to 0. At the next time, it will just look something like this. So it just shifted. And this shift is determined by omega t. It has shift an amount delta z, the maximum shifted by delta z. And you see, for the maximum point, if you just pick up any one of the maxima, let's say this at t equal to 0, we have a maxima over here. And for this maxima, kz minus omega t is 0. This is equal to 0 at every point. So this tells me that z over t, which is equal to omega over k Okay, so this omega and omega over k would tell me the velocity of this wave. So what we are asking now is it possible that the Maxwell's equations have a wave-like solution? The waves are nice because they can just go until infinity. That's what we are looking for now. And once we determine under which conditions we have this wave, we can talk about the speed of this wave. What is this speed of this wave? So this is what we are looking for. The electric field will be in the x direction. The magnetic field is in the y direction. And the velocity of my wave is in the z direction. and its magnitude is given by omega over k. And so if we can determine a relation between the magnitudes of omega and k, we can answer the question, what should be the speed of this wave? And what we will see is the speed given by this expression has to be equal to 1 over the square root of mu 0 epsilon 0. So initially, this relation, I mean, it can be just a coincidence. But we will see that the Maxwell's equation allow us to write down, allow solutions of electromagnetic waves that move at this speed. And in fact, this is one of the reasons why we identify these light waves or this laser as just an electromagnetic wave. They have the same speed. This laser light and the waves predicted by Maxwell's equations, they have the same speed. Well, we can also prove that they have the same energy, the same momentum, all the same properties. So we say that this laser light is nothing but an electromagnetic wave, or similarly for the lamps. Now, okay, so we have a solution. The next thing we have to prove is that, do they satisfy these equations? So that will be kind of the tough part. Now, what can you say about the electric field lines at a given instant? At a given time t, what do the electric field lines look like? At a given time, let's say at a given z, at a given point, at a given z, at a given time, what is the direction of the electric field line? In the z direction, its magnitude. Does it depend on x or y? It's just E. It's in the same direction at a given z at a given time. So we just take a photograph of this electric and magnetic field at a time, and we just look at a single point along z. The electric field is just constant. It's always pointing in the same direction. Remember, the electric field lines, they're always tangent to the electric fields. So this tells me that the electric field lines themselves at a given z that passes through a given z and at a given time, they always point in the same direction. They're just straight lines. Electric field lines are just straight lines. Of course, at different z, at one point the electric field lines might be straight lines in the plus x direction. At some other point they can be a straight electric field lines in the minus x direction. But nevertheless, at a given point, they are just straight lines pointing in the plus x or a minus x direction. The same holds for the magnetic field lines. The magnetic field lines, they go until infinity either in the plus y direction or the minus y direction. Now, the important thing is that neither the electric field lines nor the magnetic field lines, they don't terminate. They just go from minus infinity to plus infinity at every point. Well, at some points they just point in this direction, at some other points they point in the other direction, but I know that they are always parallel to each other and they go from minus infinity to plus infinity. Either from minus infinity to plus infinity or from plus infinity to minus infinity. So those are my electric field lines. But if the electric or magnetic field lines, they start from minus or plus infinity and go to minus or plus infinity without terminating at any point, it just tells me that E dot ds is equal to 0, B dot ds is equal to 0. So these solutions, they automatically satisfy two of the Maxwell's equations, two of them. Now we still have the other two to verify. So we are guessing a solution. Do they satisfy this equation? And also do they satisfy this one over here? If they are actually solutions of these Maxwell's equation, they have to satisfy all four. We know that they satisfy these two, they should satisfy the other two. Now let's look at the other two. E dot dl should be equal to minus d phi b by dt. Let me plot x and y axis. Now this is x, this is y, and this is z. Now the electric field lines are on the x-axis. So they will look something like this. Now the magnetic field lines are on the y-axis, and whenever the electric field line is 0, the magnetic field line is also 0. Whenever the electric field line is at a maximum, the magnetic field line is also at a maximum. So magnetic field lines, they will look something like this. Just think of it as a three-dimensional plot. This is the magnetic field at that point. This is the electric field at that point. Okay, just note one thing. Now, these are electric and magnetic field lines, you can say, along, for example, at this point, this is the electric field line, this is the magnetic field line. The electric field line doesn't start from this point and go to that point. We are talking about electric field lines at this point only. Although we are just showing the y and the x-axis, the electric field at this point might have a different value. Well, it will not, because we are assuming the electric field doesn't depend on x, it depends only on z. Now we want to prove this one. B dot dl, or let's start with the E dot dl. This should be equal to minus d phi b by dt. We have to choose some closed loop to evaluate this E dot dl, and then we have to calculate the flux that goes through that loop. Now, for every loop, this equation should be satisfied. Yes? They don't. You see, you are probably saying that, okay, here I have an derivative, so if the magnetic field goes as a cosine, then the electric field should go as a sine. Is that what you're reasoning? Why do you think they should have a phase difference? Okay. So at the peak, the rate of change of the magnetic field is 0. So electric field should be 0. But you see, okay, it's like your reasoning is the same thing as saying, okay, if the magnetic field is cosine, the derivative will be a sine, so the electric field should be a sine. So when cosine is a maximum, sine is a minimum. So they're basically the same thing. But you see, we are not equating the derivative to the magnetic field. We are equating the derivative to the electric field. Sorry, we are equating the magnetic field to the integral of the electric field. So if the magnetic field is a cosine, the derivative will be a sine function. And the integral of this, which function is a sine? Well, the integral of cosine is a sine function. So they both have to be sine functions, or they both have to be cosine functions. That's why they have to be a maximum at the same point. Now, let's just imagine, okay, let me draw a simpler picture over here. This is my x, this is my y, this is my z. I will draw my loop on this picture. Now, the magnetic field is on the y-axis. So I would rather choose a loop. No, okay, this is x. This is x, this is y. I will choose such a loop. it is perpendicular to the y-axis to the magnetic field so that the flux will be non-zero. That's why I'm choosing in this direction, in this plane. Now let's start with E dot dl. So let's say this is the point Z, this is the point Z plus dz. And remember, the electric field is in the vertical direction. So there's no contribution from this horizontal pieces, neither from the top nor from the bottom. I only get contributions from this vertical and the other vertical. Now the electric field, let's say, is pointing upward at this Z point, so I get a positive contribution from E dot dl from here, and a negative contribution from the E dot dl from here, because the electric field is pointing up, let's say at this instant, and the line element is pointing down. And let's just assume that this height is h. Now this will be the electric field at Z plus dz times h plus minus the electric field at Z times h. Along this line, I have to take the electric field at the point Z plus dz. It only depends on Z. Along this line. And when I'm coming back along this line, I have to take the electric field at the point Z, not the Z plus dz. So this will be equal to this difference which is nothing but derivative of the electric field with respect to Z times dz times h. You see, if you look at this difference and divide it by dz, you just get the derivative of the electric field. I just divided this difference by dz and multiplied by dz. So this is the left-hand side of this equation. It is already looks nice because if you look at here, dz times h is nothing but this area over here. So in this flux, the definition of the magnetic flux, we already have this area. So they will cancel eventually when I write down the equation. Now what about this flux? Now, if the electric field is in the plus y direction, the plus x direction, then we know that the magnetic field is in the plus y direction. First of all, is this a positive flux or a negative flux? It's a positive flux. Just curl your fingers in the direction of your loop. So this is the positive direction of the flux. And since we already assume that we are at such a Z that the electric field is in the plus x direction, the magnetic field will be in the plus y direction. So the flux is positive. Phi b will be nothing but b at Z dz times h. Well, it doesn't have to be at the point Z. I can take the magnetic field at the point Z plus dz or anywhere in between. But eventually I will take the limit as dz goes to 0. And so the magnetic field at this point or at any other point in this very small thin rectangle, they have more or less the same magnitude. So that's why I just take the value of the magnetic field at the point Z. You can take the magnetic field at any point inside this rectangle. Now we know that this integral, this one, should be equal to minus d by dt, the magnetic field at Z times dz times h. So again, these two will cancel each other. dE by dz will be equal to minus dB by dt. Okay, this is one equation we have. So you mean if we choose a, what do you mean? What do you mean? So you mean, so this is a point where the electric field is maximum? Or what do you mean? So this is a point where the electric field is a maximum, the magnetic field is also a maximum, right? So you are saying that since the magnetic field will be a maximum, the derivative of the magnetic field with respect to time will be 0. But so will be true for the derivative of the electric field with respect to z. Since it's a maximum, as we move across to z, it will not change. Now this is our final expression. Now we already know what our E and B fields are. Let's say this is Ex in the x hat, this is By in the y hat. Let me be more precise. Then here, these are nothing but the x component of the electric field. And this is nothing but the y component of the magnetic field. Well, I already know what they are. I will just take the derivatives and put them over here. I know that the Ex is in its amplitude E times cosine kx minus omega t. So this tells me that minus k E cosine kz minus omega t should be equal to minus b omega, no, this is sine. Sine kz minus omega t. I already know the expressions of E of x and B of y. I just took their derivative with respect to z and time t. This is what I get. Sines, they will just cancel. So I will have E times k is equal to B times omega. Now, I just guessed a solution which had many free parameters in it. E, I didn't know. B, I didn't know. K, I didn't know. Even omega, I didn't really know. So this tells me that if that is a solution of the Maxwell's equations, those unknown parameters should satisfy this relation. Now, this is one relation we have. Now, if this is satisfied, then we also satisfy the third Maxwell's equation. If that condition is satisfied, this is also true. So there's now the last one that we have to solve for. Okay, so these are the Maxwell's equations we have. Our guess already satisfied this one, this one. We had determined the condition under which this is also satisfied. Now we have the last one. So does our solutions, under which condition does our solution satisfy this equation? X, Y, and Z. And we have to determine a condition under which this is also true. Well, we will basically do the same trick. We will just assume a simple path in which we can evaluate this integral and also this derivative and equate the two. Now, the electric field is pointing in the along the x direction, so we would better choose a surface to calculate this flux, which is perpendicular to the x-axis. So I will just choose such an area, such a loop. And I will, let's say, just go around, in this sense, around this loop. This is the point Z, this is the point Z plus dz. And these are perpendicular. This loop is in the YZ plane. Now, as in the previous case, let's first start with this one. B dot dl. Again, remember the magnetic field is only in the y direction. There is no component along the z direction, so there is no contribution from this one, neither from this one. Let's again just assume that for simplicity, the magnetic field is in the positive y direction. So we will get a positive contribution from here. This is By at the point Z times L. And we will get a negative contribution from here, minus By at the point Z plus dz times L. And as in the previous case, divide by dz, multiply by dz. This is nothing but minus derivative of By with respect to Z dz times L. Again, this is nice because here we have dz times L, which is the area over here. The flux, the electric flux, will also contain the area. I will cancel, and I will get another relation. Now, for the electric flux, is it positive or negative? It's pointing up. This is my loop. Just wrap your fingers around the loop. So if the electric field is in this direction, in that case, we have a positive flux. Just for the sake of simplicity, we just assume the magnetic field is pointing in this direction, in the y direction. So at the same point, the electric field is pointing in the plus x direction, so we have a positive flux. This will be just Ez times dz times L. Again, since I will eventually, this Ez can be, in fact, the electric field at any point inside the loop. The loop is very narrow, very thin, so the electric field doesn't really change from point to point. And eventually we take the limit in which the area of this loop goes to 0. And so we have the left-hand side, we know the right-hand side. Just put these expressions over there, and we would get minus the derivative with respect to y of the magnetic, with respect to z of the magnetic field, should be equal to mu 0 epsilon 0 dEz by dt. This is our equation. And again, we know the values of By and Ez. Just put it over here, take the derivatives. This will tell us that B times sine, no, Bk times sine kz minus omega t should be equal to mu 0 epsilon 0 E omega times sine kz minus omega t. So now the sines, again, they will cancel, and we have another relation between B, K, E, and omega. So from this one we have Bk should be equal to epsilon 0 omega 0 E omega. This is our last equation we derived. Before, we already had another relation. B omega is equal to Ek. That is mu 0. So I have these two equations. I can just divide side by side. Just divide side by side. The B's will cancel, E's will cancel. So with that K over omega is equal to epsilon 0, mu 0, omega over K. Remember, omega over K was nothing but the velocity of my wave. So 1 over C, I'm just assuming this is a light wave, so I'm just looking for whether the Maxwell's equations predict a light wave or not. So omega over K is the velocity of the wave, so 1 over C should be equal to epsilon 0, mu 0, times C, or C squared has to be equal to 1 over epsilon 0, mu 0. So what this actually shows us that there is a solution for the Maxwell's equation in the form that we predicted, we just guessed, as long as its speed is given by this relation. And furthermore, if you look at this expression, B, the second equation over here, B times omega over K should be equal to E. Or E should be equal to C times B. So the magnitudes of the electric and the magnetic components of this wave should be related by C. Furthermore, its speed, the C, should be 1 over epsilon 0 mu 0. So now we have proved that the Maxwell's equation have wave solutions which move at this speed. And the question is, in which reference frame? When we were discussing mechanics, we always said that the speeds are frame dependent. Then in which reference frame is this? If our original assumption in mechanics is true. And after the observation that this doesn't really hold for light, we had the road to the discovery of the special theory of relativity. But now, I mean, we added these corrections to our Maxwell's equations. You see, these are our Maxwell's equations. Now, we try to make our equations consistent with what we know from mechanics. So we had to add this term so that changing magnetic field should create the electric field. We had to add this term also to take into account cases in which the current is not continuous. There's a point at which the current stops. But now we ended up having a theory which doesn't seem to respect Galilean relativity. So we have to fix it. Our equation also satisfies this one now. Now, we will not fix it this semester. You will study it in modern physics next semester. Or, no, next year in the spring semester. So that's where you will be studying the special theory of relativity. Now, any last questions? Now, I mean, from mechanics, from Galilean relativity, we said that in every inertial reference frame, the laws of physics should be the same, the velocities should be different, but the acceleration should be same. But now we have a speed from our Maxwell theory, which apparently should be valid in every reference frame. But Galilean relativity tells me that velocity is a frame-dependent quantity. So either Maxwell's equations are wrong, or Galilean relativity has to be wrong. And it turned out that it was the Galilean relativity which was wrong. Okay, next Thursday I will be about these Maxwell's equation. We will be discussing the energy transport. Okay, we know that if there's an electric field, there's a magnetic field in this wave, it carries an energy. So electric and magnetic fields themselves carry energy. With what speed? Well, if they have energy, they should also have momentum. And what is their momentum? We will see that.